So welcome. So I know that time is of an essence, so I'm going to do an overview of this next chapter, and I'll post it. So this next chapter is on one-dimensional motion, and it's the second part of one-dimensional motion. We've already done about the number line, and we've done about how to find displacements and distance traveled, and we know how to do the velocity versus the speed, and we know how to do the acceleration versus the pickup, and we know how to do instantaneous velocity and instantaneous acceleration, and we've learned how to do graphical analysis. And we treat all those just as independent journeys, and now we're going to put things together as a constant acceleration journey. And the reason why we care about this is because it is it's mathematically accessible, and also it's very important because that's the way gravity works. Not only gravity, but that's certainly the way that gravity works. So what we say is, for constant acceleration, the big idea is, and there's a family of graphs for constant acceleration. So if you have one particular acceleration versus time graph, it causes a very specific velocity versus time graph, which causes a very specific displacement versus time, or position versus time graph. They go together in a family. And then we can derive a family of kinetic equations from these graphs, and then we can derive the same family of kinetic equations using calculus. So some people prefer the calculus approach, some people prefer the graphical approach. We can use the family of kinematic equations. Once we've got them, either way, once we've got them, we can solve one-dimensional motion problems, assuming that the acceleration is constant. And now we could have constant acceleration in a machine tool. We could have constant acceleration in space. But we can also have constant acceleration near the Earth's surface. And we call that situation when we're near the Earth's surface, we call it free fall. So we talk about free fall. And we talk about two-dimensional motion under this situation as being projectile motion. So there's free fall and there's projectile motion. And these they're kind of interesting. They're basically the same mathematics, the same physics principles as we use in the first part of this chapter, but in this second part, I don't have to tell you as much because you know the acceleration due to gravity and you know which direction it points. And so we go on. There's not an awful lot of teaching in this, but there is a fair amount of practice because you're applying the same equations over and over again, but you've got to build your visualization skills. So let's start talking about these equations. So here's a situation where I'm drawing an acceleration versus time graph. I'm assuming that zero acceleration is there. And so this is a positive acceleration. And what that means is that whatever velocity I have to add on a certain amount of velocity every second. And if it's a positive acceleration, I'm adding on a positive number. So if this was, say, 3 meters per second, and my acceleration was equal to 2 meters per second every second, which is 2 meters per second squared, I would add on +2 every second. So if that was after 1 second, this would be +5, and if this was after 2 seconds, that would be +7. If this was after 3 seconds, that would be +9. So that would be 9, and this would be 3 seconds, and so on. So clearly, if I'm adding on the same amount each time interval, I'm going to get a straight line. So if I have a constant acceleration, I must have some kind of horizontal acceleration versus time graph. And that means I must have some kind of straight line sloping velocity versus time graph. If the acceleration is greater, more positive, I'll get a bigger slope. If the acceleration is less positive, I'll get a smaller slope. If the acceleration was 0, I would have a 0 slope. If it was a negative acceleration, I'd get a negative slope, and so on. And then, yeah, I wish I'd not done all that now. Let me see if I can find an eraser. Hold on. Yeah, there's an eraser. So let's get rid of most of that. And then let's go back here. And then say, okay, so that's my diagram. Fair enough. I know how to deal with it. And let's go to pen. Yeah. Now, if I want to know the distance traveled or the displacement, then I need to get the area under the curve. Remember, this is in meters per second, and that's in seconds. So if I multiply them together, what I get is just meters. So that's the amount of displacement in the first second, and that's the amount of displacement in the second second. Let's change the color pen. Now that I've found out how to do it, let's change the color pen so I can contrast this. And then for the third second, we'd have, let's go here, let's go green, and then that. So I have 3 different bits. And so basically what I end up with is, I'm going to finagle it here, but there's the value I got from my green area. And it was bigger than, and not just linearly bigger, it was noticeably bigger than what I got from my second value. And go back to red. And that was noticeably bigger than what I got from my third value. So this thing is increasing. It's following a parabolic path. So, and I might have started at a different address, in which case it would be the same curve starting off from a different address. So where you begin on these things doesn't particularly matter for these two. I could start off at 0 velocity. In this case, I started off at a positive velocity. In this case, I started off at 0 position. And now I'm starting off at, say, plus 10 meters. But it's got to have this shape. So these 3 types of curve go together. Okay. And so we can look and say, well, hold on, which one of these makes sense for being a constant acceleration graph? And, well, that's certainly not constant acceleration, because constant acceleration goes horizontally. So that's not going to be a constant acceleration graph. For this next one, now I'm looking at velocity versus time. And my velocity is not changing linearly with time. So that cannot be anything to do with a constant acceleration journey. My displacement, and we can argue about the shape of any curve, but you know, you gotta go with the flow here. That looks pretty well parabolic to me. So yes, so yes, that's going to go with a constant velocity journey. This is certainly a constant velocity. This is a constant acceleration journey. This is certainly a constant acceleration journey, so that one also. This is a constant acceleration journey. The velocity is changing linearly with time. It's a negative slope, which means it's a negative acceleration. And this again looks like one of these parabolic curves, and so that will also work. So there's a variety of shapes, just to fill things out, you know, just to give you some contrasts. Where are we? I could have had a displacement versus time, and my displacement versus time could look like that. This is position meters, really, and this is time, and you can see it could look like that, or it could look like that, or whatever. And my slopes, you know, for my velocity can be positive or negative. Cool. So let's do a little bit of derivation, and basically what this says is, so if we look back at this graph, we see that, well, there's an example of a velocity versus time graph. I like velocity versus time graphs because if I look at the slope, I get the acceleration, and if I look at the area under the curve, I get the displacement. So it enables me to talk about both aspects, all 3 aspects of the journey. If I look at this graph, I can infer from it things to do with acceleration. I can infer from it things to do with position. So it's a good one to start with. This is a positive acceleration. It doesn't matter about that. What matters is it's a straight line. In velocity versus time, it's a straight line. And I say, well, my y position is equal to the slope times my x position plus the y-axis intercept. That's a straight line graph. Well, let's infer this. This is my y position that I'm ending up with, so that's VF. And my slope, well, my slope is A. So there's my slope. And then my x position. So this is new notes, old notes. In the old notes, I call this T. The changed big, and I could put down T if I started at 0, but I'm not always going to start at 0, so I'm going to call that delta T. And then plus my y-axis intercept is VI. So I learn, you got to learn these. VF equals VI plus A times delta T, the duration, the time interval. Okay, let's look at the same graph, and now let's say, well, what about the area under the curve? That was supposed to be displacement. Well, the area of this is a trapezoid. So it's the average height times the width. So we have the two heights added together plus the width divided by 2 times the width. So I get a half VI plus VF times the time interval, the time interval, delta T. And you can imagine what I've done basically is I took the average velocity, which is that, and you could argue and say I took that little area there and I tucked it in under there, and no, look, it's a rectangle. And that's where all that comes from. So, okay, so I learn my displacement is equal to half VI plus VF times the time interval, my duration, if you like. Okay, let's do that again, but this time don't think of it as a trapezoid, but think of it as a rectangle. So I have a rectangle and a triangle. So here's my rectangle and here's my triangle. And of course the area would be the base times the height for the rectangle. So that's that bit. And then if I go down here and I go to blue, say, plus the area of that triangle, and that's that bit. And these x's, I'm sorry, it's like, think of them as being multiplies. Or if you prefer, you can put them in parentheses, Just like that. And this height, of course, is that guy, whereas this height is that guy. So that's pretty good. And so what I say is, well, we had a half. So what I say is I had this h, which is VI, times delta T, that's my width. So that's that guy, which was that guy. And then over here, I can say, well, this is a triangle, so it's a half. This height here is VF minus VI times delta T. So that's that guy, which is that guy, which is that guy. Cool. And then we do a little bit of finagling, and I'll explain why in a minute. But what we say is, look, VI times delta T plus, I'm going to say half VF minus VI times delta T. I actually go, well, down here, I say, well, VF minus VI is equal to A delta T. And I substitute that in, so A delta T for that guy. And so I end up with a half A delta T squared. So so VI delta T plus 1/2 A delta T squared. And I'll tell you, the reason why we're doing that is because I want this equation to have everything in it except delta x. And I want this equation to have everything in it apart from A. And I want this equation to have everything in it apart from V final. And I want this equation to have everything in it apart from delta T. So if I think about it, I have VI, VF, A, delta T, and delta X. They're my 5 parameters that get related, and each equation relates 4 of them. So it's nice if I have one relating those, and another one relating those, and one relating those, and so on. So that's why we do that manipulation. It's not that mathematically that first step was not correct. It is correct, but it's so that these things will work out a lot easier. And then I do some pure math. I just kind of like play with these derivations, and you can look at them if you like, but basically we end up with VF squared equals VI squared plus 2A delta X. You must, absolutely must, know these 4 equations. You gotta know them. You just cannot make progress if you don't know them. So learn them, get to the stage where you can be woken out of a deep sleep and you'll know them. Okay. Mathematically, I could say, well, A is equal to dv by dt, and v equals the integral of integral of ax dt plus a constant, and we can just play this game mathematically, and it will eventually get us there. And for me, I'm a visual thinker, so I think a lot more in terms of the graphs. I think it's so elegant. It's like, you know, it's what the Greeks used to do. Whereas this is what Leibniz and Newton used to do, so you take your choice. It comes out as the same answer. Let's do some. So at t equals 2 seconds, a blue sports car is at rest. So here's my blue sports car, and my velocity is equal to 0. And now notice the time. Let's put the clock inside. The clock is still, well, actually, I've got to be careful here. Later on, I'm going to be using numbers inside boxes as mass. So I'm going to say down here, t is equal to 2 seconds. At t equals 6 seconds, so t is equal to 6 seconds. The blue square has a velocity of minus 12 meters per second, so it's going in that direction, and it's minus 12 meters per second. And then what is the constant acceleration for this journey? Let's call this VF, because it comes afterwards. Notice VI need not start when the clock is 0. It's very contextual. You've got to read and visualize and then figure out how to use the equations. To begin with, put down what you know. Make your list. VI is equal to 0 meters per second. Delta, whoops-a-daisy. Delta T is equal to T final minus T initial, which equals 6 minus 2, which equals 4 seconds. VF is equal to minus 12 meters per second. And then what's the next thing? Oh, I need, what is the constant acceleration? A. I don't know. I find that by drawing that list, it jogs my memory. And I go, oh yeah, well, that means VF is equal to VI plus A delta T. And on people's papers, on a test, I'll find they write down all 4 equations in the corner, and then they figure out which one they need. That's fine. You just can't come in with a piece of paper with all 4 equations written down. That's not allowed. So you've got to know them in your head, and you can write down the first thing as soon as you walk in, but it's got to come out of your head. So then you say, okay, minus 12. I don't substitute, and I don't rearrange and then substitute. I substitute and then rearrange. I like to, it just means sometimes things that look hard in letter form look easier in number form. That's 0 plus A is what I want, times delta T is 4. Most common mistake is people, especially if they don't have a diagram, and especially if they don't have a list, they look up here and go, oh, I need a time, oh yeah, I'll use 6 seconds, ignoring the fact that you didn't start at 0, you started at 2. Which is why we don't start at 0. I mean, you know, I'm a teacher. The reason why I don't start at 0 is to find out, are you just taking the second time, or are you looking at the time interval? Because that's what you need. So then we say, well, A is equal to minus 12 over 4, which equals minus 3 meters per second squared. Put it in a box. You won't have multiple choice, so, you know, yeah, it happens to be that one, but you don't have multiple choice. You're just going to have a blank sheet of paper. So pretty straightforward, one with practice. Notice well, just there it is. It is what it is. Why did I know that this diagram should be on the right and this diagram should be on the left? I have no idea where this thing is. I just know it's happening at a later time, and I chose to put it to the right-hand side. So I didn't actually do a formal number line and have positions because I don't know the positions, but I did have a diagram, and I think that's really important. T equals 3 seconds. A red truck has a velocity of, so here we have our red truck, and it has a velocity of VI equals plus 7 meters per second. And T equal 3 seconds. The red truck has a constant acceleration. So now I'm given the acceleration. How shall I show it? I'm going to show it as a diagram. Let me show you something, just by the by. I'm rushing a little bit. Maybe that's not such a good thing, but I just want to show you something. So let's have this. This is going to be -2. What is the velocity of the truck? What is the velocity of the red truck? So, sorry, let me get back in the same colors. So here's my truck, and here's the velocity of the truck. And it equals, I don't know. And this time is equal to 9 seconds. And I'm going to be a little bit more devilish as well. I'm going to erase. I'm going to come here. I just want to show you something. Come along here. If you have one of those click pens and you say so t equaled 3 seconds, and then down here t is equal to 9 seconds, and this is a t final and this is a t initial. I don't know about you, but having different colors really helps me distinguish things. I don't need it for everything, but certainly for my diagram it's really helpful. So I go, well, VI is equal to plus 7 meters per second, and I want VF, and my time interval is equal to t final minus t initial, which equals 9 minus 3, which equals 6 seconds. And my acceleration is equal to -2 meters per second squared. And I say, let's have a look. VF equals VI plus AT. Oh, not such a good teaching example because I'm using exactly the same equation, but VF equals VI plus A delta T. So VF, at least I'm looking for a different thing. VF is equal to VI, and that was plus 7, plus A, which is -2, times delta T, which is 6. So VF is equal to 7 minus 12, which equals -5 meters per second. Okay, so there we have it. What went on? What went on is I started off with a positive velocity and a negative acceleration. Should have put A is equal to. And that means I'm slowing down. And at some point I must have stopped, and then I started coming back. And so by the time I was at 9 seconds, I had a negative acceleration still because it's constant, but I had a negative velocity as well. So now I'm speeding up, going in a negative direction. And it's a really good idea if you can go beyond getting just the right numerical answer with the right units and trying to visualize, because the more you practice visualizing, the better. Cool. Red truck has a velocity of 15 meters per second when it crosses the starting line. So let's do a track, and here I'm starting line, and my truck has a velocity of plus 15 meters per second. So it goes in that direction. And this is my VI. And then it has a constant acceleration, so my acceleration is equal to minus 3 meters per second squared, so that's pointing in that direction. What is the velocity of the red truck when it is a displacement of plus 5 meters? So here's the ending line, and I want the velocity, which would be the final velocity, and this displacement, delta x, is equal to plus 5 meters. So I say VI is equal to plus 15 meters per second. Delta X is equal to plus 5 meters. VF is what I want. And then A is equal to minus 3 meters per second squared. And I say we have what equation we're going to use. We're going to say VF squared equals VI squared plus 2A delta X. So VF squared is going to be what I want to find is equal to VI squared, which is 15 squared, plus 2 times A is minus 3 plus 5. Notice how I'm using signs. I just didn't do it there. I'm using signs on the things, positive or negative, because it's part of the value. It's not 15, it's plus 15, because it's going in a positive direction. It's not 3, it's minus 3, because it's pointing in a negative direction. So VF squared is equal to 150 plus 75 is 225. Hope I did that right. Plus, going to be minus 2 3s are 630. So VF squared would equal plus minus 30. So VF squared would equal 195. I'm going to get my handy dandy little calculator, clear it on, and I go second square root 195, enter. I'm getting 13, oops, sorry, that equals 195. So VF is equal to 13.96, which now meters per second. Now you've got to be careful here, okay, because it's the square root of a number, and the square root of the number has 2 possible values, positive and negative. Now that might seem like a mathematical nicety, but what's going on here is this thing is, look at the velocity. The velocity is, oops, daisy, sorry about that, let me get back. I think I'm there. So the velocity is, so the object is going to the right. It has a positive velocity and negative acceleration. So it's going to the right, slowing down. It passes the 5 meter mark. It keeps on going. It stops and it comes back. So in that direction, it is plus 13.96 meters per second. And later on, it comes back and it's minus 13.96 meters per second. And both of them are valid answers. And sometimes, actually, if this is a multi-step problem, sometimes you've got to pick the right one. And you pick the right one from the context, not from just the mathematics. So watch out for that. That's a level of sophistication that's beyond just plugging around. 13.96 is 14, so there's my answer on that. Cool. So we did three examples. So practice, practice, practice. When you get comfortable with that, then you can look at this next bit, which is the same, except that this is when we're in free fall, and free fall is basically a freely falling body is an object that moves under the influence of gravity only, regardless of its initial position. You can throw it up, you can throw it down, it can be traveling up, it can be traveling down, it's still in free fall if only gravity acts on it. objects thrown upwards or downwards, and those released from rest are all falling freely once they are released, provided air resistance can be ignored. We disregard air resistance on all objects. All objects fall towards the Earth with the same acceleration. Once they are in free fall, all objects have an acceleration downwards equal to the acceleration due to gravity, which is 10 meters per second squared. So it's important. Yeah, you might be traveling upwards, but you still have the same weight, so you have the same acceleration due to gravity. And we might be stationary at the top of our journey, no velocity, but we have the same weight, so we have the same acceleration. And we might be plummeting downwards, going faster and faster downwards, but we have the same weight, so we have the same acceleration. Link acceleration to the net force on the object, the overall force on the object. Now, let me talk about something just for a minute, briefly. So this is a big, heavy object, so you can imagine it's got a big weight. And this is a tiny object, so it has a little weight. So how can they have the same acceleration if I'm saying link the acceleration to the force on the object? Well, this is a big weight, but a big mass, which means it has a big inertia. So the two effects cancel, and this is a little weight and a little mass, which means a little weight, little inertia. And so what you find, I'm going to jump ahead a little bit, but A is equal to F over M. You might be familiar with F equals ma. So A is equal to F over M. So yeah, big force, but a big mass. So it cancels to 10, pointing downwards. And this is a tiny force, but a tiny mass. And so it cancels to 10, pointing downwards. At this stage, just know the acceleration due to gravity is minus 10 meters per second squared. So a typical scenario, diver standing on a board, jumps up, goes into the water. Forgive the sideways motion. You've got to, visualize it somehow. We ignore that. So then I say that the diver's acceleration is minus 10 meters per second squared throughout the journey. When the diver steps off the board, there's some language here, steps off the board. Well, they didn't jump up and they didn't pull themselves down, so the initial vertical velocity is 0 meters per second for a step. The diver has the same speed passing on the way up as on the way down. Whatever that speed is, it's the same, because what gravity takes away from your speed on the way up, it gives you back on the way down. So if this is plus 10 meters per second going up here, this is minus 10 meters per second going down there for the velocities. The speeds are both 10 meters per second. And if it takes 2 seconds to get to the top, it'll take 2 seconds to get back again. It's a very symmetrical relationship because there's no air resistance. And finally, the final velocity of the diver is her velocity just before she reaches a point of interest. So typically I'd say, what's the final velocity here? And a lot of people would say 0 meters per second because she just hit the floor or she hit the water or something. And it's not, because once she touches the water, she's no longer in free fall, and so my journey has already ended. My journey is the free fall journey. And so I'm not going to spend time telling you that. I'm just going to say, what's her velocity at the end of the journey? And from doing this practice, you have to know, oh, it's the end of the free fall journey. And so it's the velocity just before she reaches the actual surface, so that there's another force acting on her so that her acceleration is no longer the same. I could end the journey there. I could ask you a question about starting here and ending there, in which case that would be the end of my journey. I could ask you a question about starting at the top and ending as she passes the board, in which case that would be the end of my journey. Or I could ask you a question about what is her speed when she passes that point, which is so many meters below the surface, in which case that is the end of my journey. So there's not one diagram, one problem. There's one diagram and probably 16 problems I can ask you. So don't try and remember the answer, remember the approach. The displacement produced by the journey is negative if the final position is lower than the initial position. So that is a negative displacement. You've got to be careful about your signs. If you're still in the habit of saying, oh, it's 5 meters below, that's 5 meters, you're going to get tripped up. If it's 5 meters below, it's minus 5 meters because you're starting here and you're ending there. So watch out for that. There's an awful lot of, this is like stress testing. It's like they do with banks. It's like you get an awful lot thrown at you at once and they're looking for cracks in your understanding. Diver steps off the high board. High board is 5 meters above the water. So here's the high board, here's the water, and that there is 5 meters. I don't know where the beginning and the end is, so I'm just going to put down 5 meters for the minute. How long does it take her to reach the water? So she goes there. So this is the start of my journey, and this is the end of my journey. Now I can say, oh yeah, okay, that means that that displacement from the beginning to the end is equal to minus 5 meters. And I make my list and I say, well, displacement is equal to minus 5 meters. I can say my acceleration is minus 10 meters per second squared. I can say that my initial velocity, vertically, we're all talking vertically now, she steps off the board. That means it's 0 meters per second. Didn't jump up, that would be positive. Didn't pull herself down, that would be negative. And I want the time interval. So I look at this and I go, oh yeah, well, this is fine. Delta x is equal to vi delta t plus 1/2 a delta t squared. So minus 5 is equal to 0 times delta t plus 1/2 times minus 10 times delta t squared. So minus 5 is equal to 0 plus minus 5 delta t squared. So minus 5 over minus 5 equals delta t squared. So 1 plus 1 is equal to delta t squared. So my time is equal to the square root of 1, which is, it might sound crazy, it might be, it might seem like plus or minus 1. What does that mean? Well, let me draw this diagram slightly again. And so what we did was we went like that. So that was 1 second. And if the clock started here, I'm sorry, I just messed up a bit. So let's go back. So if the clock started here, I'm sorry, I'm messing up on my, I clicked a button somewhere and my pen is, yeah, if the clock started here at 0 seconds, then this will be plus 1 second. Now this math doesn't know which direction you want to run time. So it's also giving you the answer for if you had negative times and were approaching the top, in which case it would be minus 1 second. If you imagine this ball, this diver was in continuous motion and they happened to be at the top of the diving board at t equals 0. So yeah, they'd go back through the water at t equals 1 second, but to get to the diving board, they had to come up from the underworld before the clock said 0. And to get there in time, they'd have to come up from the underworld, passing the water surface at minus 1 second. So it's not a crazy answer, but in this answer, we know that our time for this downwards journey would be plus 1 second. Cool. So again, a subtlety there, but it's worth thinking about. Notice, you know, you might, a good mathematician would turn around and say, oh my word, I've got to solve for t and that's a quadratic and this is going to be awful, you know. But because I put my numbers in before I panicked, that just disappears. So it becomes a much easier problem. So it's a good idea to substitute your numbers in before you start trying to rearrange. A softball player throws a ball vertically upwards into the air. So here's my softball player, throws the ball vertically upwards into the air. The ball takes 5 seconds to reach its maximum height. Comes back down again. What was the velocity? With what velocity was the ball thrown? So I know if this is 0 seconds, I know this is 5 seconds. So I know that my time interval is t final minus t initial, which equals 5 minus 0, which equals 5 seconds. I know my acceleration, as always, is minus 10 meters per second squared. And I want to know the initial velocity. I need one more thing. I don't know the displacement. I suppose I could try and find it. So there's 2 things I could think of. Remember this list, VI, A, VF, delta T, delta X. And on this particular question, we've talked about delta T, and we've talked about A, and we've talked about VI. So then that means we have to worry about, somehow we have to get delta X, which is my displacement, I don't know it, or VF. VF, of course I know VF. It stops going upwards before it starts going downwards. On a velocity versus time graph, V versus time, I start at some positive velocity. My acceleration is constant, so I get a nice straight line. And that, sorry about that, that when V equals 0, that's the top of my journey. That point there is the same as that point there. So VF equals 0. VF equals 0 meters per second. Wasn't told it, but I inferred it. VF equals VI plus A delta T. This is used often. So 0 is equal to VI, which is what I don't know, plus minus 10 times 5. So VI, I keep wanting to write VF, I'm sorry. VI is equal to, take the minus 50 to the other side, plus 50 meters per second. There's our answer. By the way, I could have got that using a table, just to show you this. So if this is V and this is T, and I know after 0, 1, 2, 3, 4, 5, I know that's 0 meters per second because I'm at the top. I stopped at the top after 5 seconds. That's what that's saying. Then, and I know my acceleration is minus 10 meters per second squared. So I got to add on minus 10 every time I go to the next section. So if I'm going that direction, I got to add the acceleration, which means add minus 10. If I'm going in the other direction, I simply add plus 10. So that was plus 10 meters per second, plus 20 meters per second, plus 30 meters per second, plus 40 meters per second, and plus 50 meters per second. So when the time was 0, I was at plus 50 meters per second. And that's the answer I got. That guy there is that guy there. 2 different ways of getting to the same thing. Well, 3 different ways, really. There's using the kinematic equation, there's using a knowledge of what acceleration represents. So there's using the kinematic equation, there's using the knowledge of what acceleration means and using a table, and then there's using the knowledge of what acceleration means and using a graph. 3 different ways of getting the same answer. A diver jumps off a high board. So here we have a high board. Diver jumps off a high board with a velocity. So my VI equals plus 15 meters per second. She reaches the water after 4 seconds, so there's my start. And she reaches the water, so there's my end after 4 seconds. So my delta T equals 4 seconds. What is the velocity as she reaches the water? So my VF is the end of my journey. So VF is what I don't know. I know VI, of course. VI is equal to plus 15 meters per second. And I need one more thing, and of course the thing I always know is the acceleration due to gravity. So then I look at these guys and I go VF equals I, VI plus AT. VF equals VI plus A delta T. So VF is what I want, is equal to VI is plus 15, plus A is minus 10 times delta T is 4. So VF is equal to plus 15 minus 40, which equals minus 25 meters per second. And that minus sign is reassuring because it needs to be minus because she's actually going downwards at the end. So practice, practice, practice on these. And there we have it. There's only so many things I can do as your teacher. In these questions, somehow you have to be able to get 4 out of, you have to be given 3 and be able to get the 4th out of 5 parameters, VF, VI, A, delta T, delta X. And if I want you to find one, I got to give you 3 of the others. And in these free-fall problems, I don't have to even mention the acceleration. I just have to tell you it's a diver. Divers live on the Earth. This is not a diver in the moon. This is a diver on the Earth. And you know, don't expect me to become like a lawyer and write a question that under all circumstances an intelligent being from Pluto could answer. There's context in here, and so you have to practice. You have to recognize the vocabulary and the vernacular. But I'm governed by math. If I want you to find one of these things, I have to somehow give you 3 of the other things. Most common mistakes, because I don't start the clock off at 0, often people put the final time in, not the time interval, not delta t, they put t final into the equations. Let's do another problem. Let's say, how long does it take her to reach the top? So now I'm starting here, but I'm ending here. And I say, oh, well, you know, VI equals plus 15 meters per second. And VF is equal to 0 because she's at the top, meters per second. And then A is equal to minus 10 meters per second squared. So delta T for this journey equals, I don't know. And I go, oh yeah, VF is equal to VI plus A delta T. So VF is 0 is equal to VI, which is plus 15 plus minus 10 times delta T. So that's going to be minus 15 over minus 10 is equal to delta T, which equals plus 1.5 seconds.